Thank you. All right, so I took a lot of work and time trying to figure out how to condense this type of information into about 5 minutes, and this is what I came up with. Write faster code. Okay, but seriously, let's go a little bit deeper into this, something that you typically don't see in Unity or C#, and that's where we're going to talk about CPU prediction. This is something that when you're writing in C++, you start learning more information about this stuff, but C# world, Unity, no. So let's say that we're grabbing variables and we have a function that's holding like 6 different variables in memory. Now, those variables each can cost upwards of almost 400 cycles from your CPU in order to read one Boolean variable from another object. 400 cycles. Now, as a reference, a square root is less than 40 cycles. And as Unity developers, we typically know don't do the square roots if you can avoid them. So how do we make this faster? Well, one is we want to try to get our memory aligned. We want to make it contiguous. We want it to show up so that the CPU can read it and pull it in quickly in one tiny chunk if possible. So in this case, we're pulling in the memory, and so if we can get our memory aligned, it'll be able to pull it up in one chunk pretty quickly. And here's the CPU prediction part. The processor would like to assume that we have written really elegant code, that our code, that even though we haven't told it where to pull its next memory from, it's going to know that you obviously wrote your code, so it's going to pull it from the next point in memory, right after what it just read. And so if you actually get there and you start asking for the next memory and it happened to have lined up, you don't even have to wait for that memory to load. That is an incredible set for performance. That's actually what drives most of ECS in Unity. So this is an example of C# running structures from just a common setup that we might see. And so inside of here, I've got a laser pointer, yay. So the car structure, just normal car structure, gets a tiny little spot in memory. There's 6 variables here, just like the last slides. And then over here I have an array, engines. This actually shows up in a different spot in memory. That's because we don't know what size it can be. It can change. So all of this information can keep changing, and so it separates them. So it doesn't have to keep rewriting memory all the time just because we changed one array. And then same thing, every one of the, wrong button. Every one of these engines has an array inside of them. So this is for hover racing. This is every engine. There's one on each corner. And so there's also thrusters for each one. So each of those thrusters arrays, there's 4 of them. That's how it would line up. And this over here is roughly what we want. How do we get it to look like that? Okay, so here's the example of how to set this up. Also, I just want to point out that I don't expect people to walk away and be able to just do this right away. There's a lot to try to remember, and so you can see a 40-minute video on this at devious.games. Okay, but over here, we're going to turn on unsafe in our C# code. So inside of it, we're going to set up a struct layout because when you're compiling code, it can rearrange the order of memory. And we're basically going to say, okay, inside of here, we're going to use a fixed byte array. But inside of this, when we say fixed, that means that we can now establish a size, which means that when the structure is put into memory, it actually generates all the memory together. So all of the bytes are now locked into one chunk of space, so when we are asking it to load this, it is guaranteed to be in that same spot, sequentially, one spot loaded after the next. All right. Let's see. Oh yeah, so then we've got 2 engine structures. Now, this is a byte array, so that's a little bit awkward. How do we actually get to this thing? We need to be able to manipulate these values. So this basically 3 lines will give it to you, but it's, again, a little bit awkward if you haven't dealt with this in C# at all before. So first of all, we create a fixed reference. This basically locks down our memory so garbage collection can't move it around anymore. And then we tell it, give us a pointer, a byte pointer to the first byte of the engines array. So that fixed byte array, we're grabbing the address of it, and we're passing it into a pointer, just the byte. Now, that is just 1 byte in memory, and that's all it thinks of it. 1 byte right here with a length of 1. We convert it, taking the bytes pointer, convert it into an engine struct pointer. And now it says, okay, well, I'm pointing to the exact same spot in memory, but it knows that the length goes out much farther because it's the full structure. It understands that there's a lot more stuff going on inside of it. Now to interact with it, instead of using dot, I'm going to be using the arrow. So engine arrow position equals. So I can get and set values. Example, Unity physics. Unity's default physics system will quite often rely on BVH or SAP. And so in BVH, that would be for static environments where you have more things that are staying locked in position. And SAP is going to be more dynamic environments. But both have an expense. Both have an expense when they're processing, trying to figure out what the relational world around you is. So in this one, last slide, is my physics system. Now, inside of this, if I have a racetrack that's going along, I can basically determine that where I am within the racetrack is a distance. And I can convert that distance into an array, or into a position or an index in the array, and just say, if I'm 10 meters into this, then I know that this is what my index will be. And then give or take 6 or whatever distance I need to gather all the triangles immediately around, I can just pull in every single triangle without having to do any complex math or structures or rely on any system that doesn't actually know exactly what my system is doing. All right, that's it.